All right, so welcome back. So I was a bit delinquent in getting you the things I promised I was going to get you after last class. My computer in my office died on Tuesday, and so I've been kind of scrambling to get everything back in order. So I'll try to have my website updated and YouTube updated. I think by either end of today or tomorrow. So I have brought in my laptop this time, so I should be able to sort this out. But apologies for that. We were talking about energy methods and the way that you can learn kind of basic things about structures by evaluating their energy. We started talking kind of vaguely about kinetic energy, potential energy, strain energy, and today my hope is to be able to take those kind of abstract ideas and make them a little bit more useful to you, immediately useful, something where we can kind of very quickly look at some equations and make some definitive statements that explain what we observe around us all the time, and probably what we observe in a way that we completely take it for granted. And to do that, we're going to start by taking our strain energy and starting to split it up. So if you remember, we defined, I'm not screen sharing, thanks. Oh. Nope, no, I am. All right, cool. So if you remember, we defined strain energy as a integral over the volume of our structure. And what we're integrating is the stress times the strain. And so we called that capital U. We said we're going to integrate over the volume of stress times strain times dV, and that will give us the strain energy in our structure. And just like we did it in mechanics of materials, it's really useful to start to kind of break up the types of deformations into their simplest components. What I mean by that is you can take a bar and you can stretch it. And you can ask, how much energy do I store in this pink bar as I stretch it? You can ask the same thing about how much energy is stored in this thing if I only bend it. So I just kind of perfectly bend this thing into something that looks sort of like a circle. You can ask the same thing for how much energy am I storing in this object as I start to twist it. And these are all the things that we learned in mechanics of materials. We didn't talk about them in terms of energies, but we talked about them in terms of, okay, what is the stress in this bar when I stretch it? What's the stress in this bar when I bend it? What's the stress when I twist it? What's the transverse stress when I bend it and it happens to be really thick and really short? We're going to do the same thing here really quickly and evaluate these things in terms of their strain. To do that, it requires us to recall what we learned in mechanics of materials, which is, well, we need the stress and we need the strain. And this approach is pretty straightforward and it's pretty powerful. So let's consider asking, well, how much energy are we storing in that body as we stretch it? And so we can kind of draw our little beam here. Oops. We can mark some axes on here, although none of this really matters for what we're trying to evaluate. We'll call this the X direction. We'll call this Z and call that Y. And we'll say we're going to just uniaxially stretch it. So we're going to apply a uniaxial stretch in the X direction. And so you can think of that as us taking a force that is uniformly distributed on that end over here. So we can call that force P. We can say that our beam is basically stuck to a wall over here. We know that at that wall, it's going to experience the equivalent reaction force, P. It's got some cross-sectional area. And there's two ways you can do this. So this is kind of important if you ever end up going and doing any experimental mechanics, any sort of structural mechanics or experiments on materials or structures where you're in lab. Actually, it doesn't really matter, in lab or in a computer simulation. You often have two choices, and they seem like they're going to lead to the same types of behavior, but it's not always exactly the same. And the choices are, you could impose a known amount of force and measure the strain. That's what's called load controlled or force controlled. Where you apply your load and you measure your strain. Or alternatively, you can do the opposite, which is displacement controlled. Where you apply some sort of displacement, we'll call it a strain right now, but usually you would apply some sort of deformation or displacement. And you would measure the force that's being exerted on this object. It seems like these are exactly equivalent, and sometimes they are. But in the case of instabilities, we talked about the three kind of fundamental ideas in structural mechanics: stiffness, strength, and stability. In the case of stability, this can make a huge difference. So for instance, when we talked about the soda can experiment, we've all stepped on and crushed a soda can. The behavior of that soda can will be remarkably different if you apply displacement control, in which it will still buckle, your soda can will buckle, but it will not crush. It'll just kind of slowly develop these little crush-like patterns around the ring of it. It'll kind of be stable in those states all the way until you can load it into its little pancake there. Most of us, when we crush a soda can, we apply a load. We literally step on it, or we stand on it, and it just goes from a soda can to being crushed immediately. The behaviors there are dramatically different depending on if you're imposing a load and then saying it can displace however much it wants, in which case it can go and then dramatically change, or imposing a displacement and just measuring how much load is required to impose that displacement. But you're saying you can't displace more than the amount I'm letting you. Seems really similar. The behaviors can be quite different. I'll try to post a YouTube video. I forgot to grab it for today, but there's these really nice ones of people doing experiments on crushing soda cans, and you can kind of see the patterns form as you load them under displacement control. But then, of course, if you load it under load control, it's just like watching the soda can get completely crushed. So we'll derive our strain energy for both of these cases, and I'll tell you a little bit about which one you're often, or at least I'm often using more frequently. So we'll start with load control. The math is really simple either way. So we remember that the stress of a bar under uniaxial tension or compression is just the load that you're applying, P, over the cross-sectional area. So we know, and we can be a little bit careful, we can say that the stress in the x direction is equal to the force. If we want, we can call this the force in the x direction. We can call it P sub x over the cross-sectional area. We also know, and I'm going to write this down just for the sake of completeness, because this integral, as I said to you before, is a little bit more complicated than it looks, because both stress and strain, are tensors. And so what this equation is really asking us to do is it's asking us to take the stress in the x direction times the strain in the x direction, add to that the stress in the y times the strain in the y, stress in the z, strain in the z, and then do that again for all the shear stresses. That's what this equation I highlighted is actually requiring us to do. But I'll remind you that if you do uniaxial loading, then our stress tensor is really simple. It's just the sigma xx component is p over a. And then the other 8 components of my stress tensor are just 0. I'm not applying any forces in the y or z direction. So everything else is just 0. Now, it's probably been a while since some of you have seen mechanics of materials, or perhaps your memory of it is a little bit foggy, but I'm sure someone is thinking, wait a minute, I remember that there's some sort of Poisson effect, and if I pull on this thing in x direction, I hope you can see this at home, it starts to shrink in the other directions. So pulling on this in one direction, I've only applied force in one direction. It causes displacements in all 3. It causes it to stretch in x and shrink in y and shrink in z. That doesn't matter here because we're taking stress and we're multiplying it by strain. So our strain tensor is going to look like delta over L. There's no shear, so these are all 0. Oops. 0. And this one is going to be like negative nu delta over L, negative nu delta over L, where that nu is our Poisson ratio. I'm writing this down for completeness, just to kind of maybe remind you of what you've learned in mechanics of materials. But I'm going to let you know right now that it doesn't matter because we're taking stress, we're multiplying it by strain, and we're taking each component. We're saying, okay, I need this times this, and I need 0 times this. I need 0 times this. So even though there are strains in the other directions, this equation, it doesn't care. It's taking 0 times those numbers. And so the math is actually really quite simple. So what we're going to do is say, we know what the stress is. We've imposed it, but we don't know what the strain is. We don't know how much the bar has moved. And so we do know Hooke's law. We know that Hooke's law tells us, so for instance, right now we don't know, actually I'm going to be more careful here. We actually don't know really any of these. We don't know any of these strains. But we do know that Hooke's law tells us that strain is equal to stress over E. It's usually written the other way. We usually say that stress is equal to the modulus times strain, but just dividing through by E on both sides. So this means we can take our strain energy equation and it becomes really simple. There's only one stress and we can represent strain in terms of that stress. So we can say, I'm going to integrate over the volume and I'm going to get that I have sigma ij times sigma ij over E. That's coming from our representation of strain using Hooke's law. Oops, I lost a half, didn't I? See, I told you I was going to lose a lot of halves. Okay. So again, this becomes 1/2 sigma ij squared over E. And we know that sigma ij has only one term that's not 0. It's P over A. And so this becomes the integral of P squared over EA squared dV. Now, this is a volume integral. I write it compactly like this, just so it's nice and neat on the board here. But remember, this is the triple integral. What we're really saying is that our stretching energy is equal to the integral. Which order did I write these in? Yep, okay. From integral through the thickness in the z direction, integral through the width in the y direction, and then the integral along the arc length in the x direction. Dx, dy, dz. This integral is straightforward to do because there's no appearance of y or z here. So we just end up with, if you integrate this thing from negative b over 2 to b over 2 in the y direction, you get b. You integrate from negative h over 2 to h over 2 in the z direction, you get h. Oops, I again lost my 1/2. So we can simplify that. We can do these integrals directly. And say I'm going to get something like HB as the integral on the length. And the cross-sectional area of a rectangular beam, A, is exactly H times B, right? It's just the integral, it's the area of a rectangle of height H and width B. And so we get to cancel these things. We can say this is A, we get an A out here and then 2 A's in the denominator, or A squared in the denominator. And so we can simplify this to say that our stretching energy is equal to 1/2 P squared over EA. I want us to start thinking about how quantities change. And what I mean by that is that what this tells us is that if I double the force that I'm applying onto this object, that quantity is going to be squared. So 2 to the 2 is 4. That's going to quadruple the energy that you're storing in the beam. So the energy required to stretch your beam, or conversely, you can think of it as the energy that you store in a beam when you stretch it, goes as the load that you apply squared. These types of conceptual ideas of, does something increase linearly with your load, quadratically with your load, cubically with your load? These types of things will help you understand what's important and what's not. What can I neglect or what can I keep? And I'm going to show you that just by looking at like the order of magnitude of these terms, we can say something that is really obvious to all of us about the behavior of thin objects. But we'll do it using math. And so that's where we're going to go with this. But I want you to, at the very least, start thinking kind of conceptually about what these equations are saying. If I apply a load, the energy that you're storing in that object will change with the square of that load that you're applying. Double the load, 4 times the amount of energy that you've stored in there. Is everyone following? Is this okay? Is this fairly okay? Cool. And if at home, let me know too if there's any questions. Feel free to jump in, and I can see the chat too. So if anyone has any chat questions. Okay. We can do this again for displacement control. This is the form that I am more typically used to seeing in evaluating the behavior of structures. I think part of the reason is it's really easy to walk around and see how much an object is deformed, and you need some sort of tool like a scale or a load sensor to tell how much force you're applying. It's easy to kind of mark and see, well, I know this thing used to be this long, now it's this long. So strain is often easier for us to observe in practice than load. And so we can look at the alternative configuration, which is displacement control. Same exact schematic, except instead of applying a P, force P in the X direction there, we're going to say I'm going to apply a known amount delta. And I'm going to think about that delta, the displacement delta, relative to the original length of my beam. So I'm going to say, in this case, I don't actually know anything about my stresses. They're going to be dependent on how much strain we apply. But I am going to impose a strain. I'm going to impose a strain only in one direction, the X direction. So I'm going to, again, this will be delta over L. And for completeness, I'll just point out that, oops, my entire strain tensor will look like delta over L, and I'm applying no strain in any other direction. So it's a bunch of zeros. Therefore, when you multiply those bunch of zeros with your stresses, you're again only going to be left with one term in your strain energy, which is going to be the term that's in the X direction. Just like we did before, we use Hooke's law. And Hooke's law tells us that sigma ij is equal to E epsilon ij. And just like we did before, let's see where, one second. And just like we did before, we can evaluate our strain energy by saying, well, here my strain energy in stretching. This is also, I'll do this. Here my strain energy is going to be 1/2 times the integral over the volume of E times epsilon ij. That's my stress from Hooke's law. So this is sigma ij. I have my epsilon ij, and I'm integrating that over the volume. Again, we can kind of simplify this. 1/2 the volume E times epsilon ij squared dV. And in this case, we're gonna do the same thing we did before. We're gonna say we know that we can evaluate this triple integral by integrating through the thickness, integrating through the width. It's gonna lead to an area appearing. So we're gonna get an H times V as we integrate through those. So we're gonna get 1/2. And if our modulus doesn't change over the x-axis, we can kind of pull that out of the integral. We can say that I'm going to have 1/2 EA times the strain squared dV. Now this one should look familiar, not written in this way, but it requires you to go back to like physics 1. freshman year. Physics 1 freshman year, you had something that was, oops, that's not a dV anymore. Sorry, that's a dx. Physics 1 freshman year, what you learn is the energy of a spring is 1/2 kx squared, right? And you can derive what the force is by taking the derivative of your energy with respect to length. And then you get that the force is equal to kx. Strain energy stored in a spring goes with the displacement squared. This is true here. Remember, your displacement is inside there. It's buried in the epsilon term. We're just normalizing an epsilon term by length. Talk about strains instead of displacements. But this is the same. It's Hooke's law. It's the same thing as you saw in freshman physics. The energy stored in a spring goes with the displacement squared. And all we've done is said, well, it goes with the displacement squared relative to its original length. So now there's two ways to look at the strain energy in stretching. So we can say that, just to kind of summarize, stretching energy you can write that your stretching energy is equal to 1/2 EA times your strain squared dx, or your stretching energy is equal to 1/2 EA times your force squared. These are equivalent. Through Hooke's law, and that's what we just showed. So in both cases, the energy will quadruple if you double the force or if you double the strain. Oftentimes you'll see, if you ever go off and do research in this area, or if you are talking to people who are more physics oriented than engineering oriented, they'll say, as an order of magnitude estimate, we can say that we can ignore those factors of 2, and we can say that our strain energy is going to scale as, and that's what this little squiggly tilde symbol means, it's going to scale as EA times the strain squared times length, or it's going to scale as 1/EA times the force squared times length. So I did something weird here, and I'll tell you what I did to get this scaling. I said, well, if I just look at this dimensionally, the integral over the length of dx is going to give me something with dimensions length, right? I'm going to get like a length here. And so sometimes problems are really complicated to dig into. So for instance, if you wanted to evaluate the behavior of a plate, plates are harder than beams, but the energy of a plate still scales like this. There's some other prefactors here. There's a Poisson effect that you have to account for. There's the numbers that multiply this are not exactly 1/2, they're a little bit different. in terms of order of magnitude estimates, for a plate, for a beam, for a shell, the energy that you'll store in that object will always scale as its area times its modulus times the strain squared times some characteristic length scale. I point this out because we're going to use this to make to help us understand some of the behavior that we see in everyday objects. But in order to do that, we have to go through one more of these derivations. So this is like a very hand-wavy mathematical approximation saying, if I just care about an estimate of how much energy is being stored in an object, I can approximate that by saying, well, that integral is, I don't know how, sometimes you don't know how to actually do this integral. Sometimes the stuff that's inside of here is not, it's either unknown or it's not exactly easy to calculate this integral, but you know that at the end of the day, you're going to get some number times the length. And this is what, if you've taken things like fluid mechanics, you learn things from dimensional analysis. How do we just evaluate the dimensions of our problem and learn some of the regimes where you see one behavior versus another behavior? It's exactly what we're doing here. Same exact process, just dimensional analysis, and it's going to allow us to know when are some things important and when are other things important. Does anyone have any questions on any of this for stretching energy? We're going to do the exact same thing for bending. It's maybe 10% harder, but it's also pretty straightforward. But it's important because it's going to allow us to gain some intuition into structures that if you have this intuition, you can get quite a good deal done in terms of estimating what's going to happen to a structure when you try to deform it. All right. So let's look at the strain energy in bending. We're going to consider pure bending. And just like in stretching, you have two options. You can either, in stretching, you can apply a load and measure a displacement, or you can apply a displacement and measure a load. In bending, your choices are you can apply a moment and measure a curvature, or you can apply a curvature and measure the moment required. So we'll evaluate both of these. All right, so we'll think about a beam in pure bending. Pure bending is like analogous to saying uniaxial extension. It means the only thing we're going to do is bend it, and we're going to bend it uniformly over the entire length of the beam. And we'll start with an applied moment. Does anyone remember the stress in a beam when you apply a bending moment? I will interpret your silence to mean negative my over I. Better? Ringing a bell a little bit? If you recall, we could get a little bit more technical and we could say, well, that moment is actually being applied in a certain direction. So let's go back to our beam. Let me just copy this thing. Hold on. So we can go back to our beam. And let's do some things here. Now we're no longer going to apply a moment. Oh, I changed my coordinate system. What a jerk. Well, shoot. What do I want to do here? Ugh. Let me keep the coordinate system and make the beam a little bit smaller. This is a really annoying way to do this. Sorry. Forgot that I changed the coordinate system. Typically, what we do is we apply a moment, positive moment, which would be counterclockwise about the z-axis, for example. That's the typical way we did this in mechanics of materials. So we would normally apply a moment about here. Because I foolishly changed my coordinate system, this looks flipped. But really what I'm saying is I have a beam. For those at home, this beam is rectangular, so the thin direction right now is in the vertical direction, and into the board towards me is the width, which is larger. So I'm going to take this and I'm going to bend it. And what I'm trying to draw there, but because of my coordinates, it looks a little bit messed up, is it really looks like I'm doing this, is I'm taking this thing, I'm saying the x-axis runs this way, and I'm going to apply a moment about the z-axis to get it to bend like this. The thing I want you to remember is in this equation, the second moment of area, I, also, you can have a second moment of area in X, Y, and Z. The second moment of area matches the direction that you're applying the moment. So if you're applying the moment in the Z direction, then you're using IZ. If you're applying the moment in the Y direction, you're using IY. So we're going to say this is moment Z over IZ times Y. So I said this one's like 10% harder than the last one. We do the exact same thing. We're going to look at the strain energy in bending, and we're going to say it's going to be 1/2 times stress in the x direction squared over E over the volume, dV. Just like before, in the case of pure bending, when you have pure bending, you only have stress in one direction. So therefore, all the other components of your stress tensor are 0. So therefore, your strain energy is just one term. This becomes, the negative sign doesn't matter because it becomes negative. Let's do this again. Let's do it this way here. It becomes 1 over E times negative mz y over iz squared integrated over the volume. And we can separate this out because this is going to be helpful to us. And we can separate this out and say this is just mz squared y squared over e iz squared. Here again, it's important to remember that we're doing a volume integral, except this time it's a little bit trickier. So our strain energy in bending can be rewritten if we pull that volume integral and we separate it into an integral over the length and an integral over the area. So if we just look at the integral over the length, 0 to L, the moment doesn't depend on Z or Y. It's uniform. It's just in the Z direction. Modulus doesn't depend on Y or Z. IZ is just a number. Doesn't depend on Y or Z. But now we can take that thing and we have the integral over the area of y squared dA. Anyone remember what the thing I highlighted in orange is? Nothing? No one? This is the definition this integral of y squared over the area is the definition of IZ. This is your second moment area. I think this is like sometimes covered in mechanics of materials, sometimes covered in statics. It probably depends on who you took it from and when you took it. But this is I. This is IZ. If you integrate over Z over the area, you get IY. And then this is how you're gonna get like that term of everyone probably remembers I being H cubed B over 12, maybe. Yeah, so it's because you're integrating over the two directions. You have a y squared, so you get a cubed. You have a well, nothing, so you get a b. But this is your second moment of area. You might remember that your first moment of area is the integral of y dA. So the second comes from the fact that this thing is squared. Anyway, that means for our case, for our purposes right now, what that means is that this IZ is in the numerator, we have the square in the denominator, we get to cancel one of them out. So our math gets a little bit nicer. So we get to simplify this to say it's going to be 1/2. Oops, actually I want to do this a little bit differently so I can write this out. You can say that our bending energy is equal to 1/2 the integral over the length of mz squared or E iz dx. Again, sorry, my Z's look like smudges. But again, the underlying kind of physics or mechanics between stretching and bending are analogous. you apply a force or a moment. If you double that, the forces or moments are squared. It leads to a quadratic, it leads to a 4 times increase in your stretching or bending. The form is kind of the same, right? It's like thing that you apply squared over material properties over cross-sectional properties. In stretching, it was load over modulus times area. In bending, it's moment squared over modulus times I, which I is a property of the area. It's just a kind of a messier property of the cross-sectional area. So the form of these are the same. So far, so good? Keep going? Okay. Just like before, if we don't apply a moment, but we apply a fixed amount of curvature, which means I'm going to take my object and I'm going to bend it to a certain radius of a circle. That this thing has a, you could imagine fitting a circle to this and saying that circle has a radius r. Curvature is the inverse of the radius of curvature. This always trips people up because they use the same word. But curvature is the inverse of the radius of curvature. So as I bend this thing, my r of my circle, so like it's probably easier to see it if I do this. Here, the r of my circle is pretty small. Oops. And as I unbend this thing, my radius of the circle is getting bigger, right? You might say, why do we need two definitions? Why can't we just use radius of curvature? Why do we use curvature? The reason is this. What is the radius of curvature of this object? Infinity. Infinity is a pain. No one likes to work with infinities. What's the curvature of this object? 0. Much easier to use. So we use curvature because this has a 0 curvature, and then no matter what you do, you're going to get a finite curvature, a number. If you use radius of curvature, you have to deal with infinities, and then that's just a huge pain to deal with. So I'll write that down really quickly, just as a reminder. So if this is the radius of that circle is r, your curvature is denoted by the Greek symbol kappa, and it is equal to 1 over r. Helps get rid of these infinities. Okay. Let's go back to beam bending. Again, we're doing a beam, it's in pure bending, and we're going to apply an amount of curvature. So you might not remember this as well. You use this in mechanics of materials when you're doing the derivation of the shape of a bent beam, which is usually called the equation of the elastic curve, or the shape of an elastic curve, which is basically like, okay, I've got my beam, it's simply supported, I'm applying some load to it. How do I plot what the shape of this thing is? You might remember having like a fourth derivative equation that you have to integrate 4 times and apply boundary conditions to find what the shape of this thing is. Maybe not. There's a constitutive relationship. Remember, constitutive means the relationship between stresses and strains. So the constitutive relationship in stretching and compression is Hooke's law. Stress is equal to modulus times strain. There's a constitutive relationship in bending too. It's just that what the constitutive relationship in bending is that the moment you apply the amount of kind of torque or moment you're applying to this thing, is related linearly to the curvature times EI. So this equation, I would not be surprised if you have forgotten that you ever were introduced to, but it looks like this. So this is a constitutive relationship. So constitutive relationships are how you connect loads to displacements, or I should say loads and moments, loads or moments to displacements or deformations. Hooke's law is a constitutive relationship. The constitutive relationship in bending says that the moment that you apply will be equal to the curvature times EI. This is just like Hooke's law. It's just for bending. So there's a linear proportionality between moment and curvature. And in Hooke's law, we say there's a linear proportionality between force and displacement. Same idea. So if this doesn't ring a bell, that's okay. But it's important. So I'm going to color it. All right. So we can use this instead of kind of going from scratch and writing down the strain energy. We can just use this to say, well, if I know what the moment is and I want to relate that to the curvature, then I can just kind of insert that into this equation, right? I have m squared. I now know what m is, and that'll allow me to write my bending energy in terms of my applied curvature. So it'll tell me if I increase kappa, how does my energy change? So I'm just going to literally insert m, which is kappa EI, into my equation there. So now my bending energy is going to be equal to 1/2 the integral over the length. I have kappa EI. All of that is squared over EI dx. And you're going to see that a lot of things are going to nicely cancel out for us, right? We're going to lose the E and the I in the denominator. We're going to be left with the E and the I in the numerator. And that means as long as my modulus and my cross-sectional area do not change along the beam. So here's an example of one that doesn't. This is just one block of rubber. The cross-sectional area is the same and along the entire length. The material is the same. So those don't need to be in the integral because they don't vary with respect to x. You can pull them out of the integral. And we can say that our bending energy is equal to 1/2. We'll do it a little differently, sorry. Is equal to EI over 2 times the integral of kappa squared dx. So it looks like it has the same form as our stretching energy. Stretching energy said, I'm going to have E times some property of the cross-sectional area times the integral of my deformation squared. Same idea. Now I just have E, some property of the cross-sectional area, times the integral of some deformation, in this case curvature, squared. The last thing I'll do before I take a quick break is I want to write this bending energy in a scaling like way, the same way we did the stretching energy. To do that, it's really important to remember the properties of I. And we'll find out why in a second. But if you remember, if you have a beam with a thickness h and a width b, I is equal to h cubed b over 12. Now remember what I said before. The second moment of area is defined as the integral of y squared over the area. And so in this case here, it's basically saying it's the integral of this dimension squared over this direction and this direction. So you get, and that's why you get an h cubed and a b. Most students can never remember which quantity is cubed and which quantity is linear. Is it b cubed or h cubed? It kind of depends on how you're bending it. Just remember that I always have a hard time trying to remind students of this, but this sheet, this is probably a bad example too. How do I want to do this? Let me say it a different way then. Let's say it as, if I'm taking this object and applying a moment about the axis that runs that way. So that means, look at my object here. I'm looking down the barrel of this object here. Okay? If I'm applying a moment about this axis here, such that this thing will bend like this, the direction that you're cubing is the one that's perpendicular to that moment. If I was to take my object, rotate it, so now it's a vertical bar, but apply the same exact moment, so that is a moment about this kind of imaginary direction coming this way. In this case, the cubed quantity is again the one that is perpendicular to the moment that we're applying. And what you would see if you were playing with an object like this is that this thing is really easy to bend when this dimension here is small. But as I make this dimension bigger, it's really hard to bend this thing. I can bend it a little bit, and then it starts to buckle. It really doesn't want to. What's happening there is the dimension that is perpendicular to the axis that I'm bending around is the one that's cubed. So changing this thing by a small amount, doubling it, leads to an 8-fold increase in its second moment of area, which means bending it is 8 times harder. I don't know if that's going to help. This sometimes just takes a little bit of practice with these problems, but this is I. The reason why I'm doing all this and pointing out what I is because we can then go back to our bending energy and say, that my bending energy will scale as EH cubed times my width times my curvature squared times some like L. This is going to be really important for us to gain some intuition on something, but before we do that, let's take a break. Think of some questions if you have any while you're on the break. You can ask them to me, or you can just take a break and ask them when we're done. Well, let's take about a 5-minute break and come back at like 10:06.
But like,
All right. Before we use these ideas to gain some, or to maybe explain some of the intuition we have about structures, I want to do one more brief calculation, and that's going to be strain energy in torsion. And I say this is brief because torsion and bending are both cut from the same cloth. They both take the same form. And this may or may not have been clear to you when you took mechanics of materials. But let's see if we can look at this really quickly. The stress in bending an object. And I'm just going to put it like an approximate or like a scaling term here, because depending on which axis you're using and which direction you're going in, it could be a positive or a negative sign. But for right now, the sign doesn't matter. I just want to show you that the form of the equations are the same. So I'm going to say that the stress in bending is equal to the moment times y over I. Now you might recall that when you take an object and you twist it, you apply a torque to the end of this object, you're going to get a shear stress and a shear strain. And the shear stress, I'm going to use the symbol sigma here, which will become more clear in a minute why. It doesn't have the subscripts that are the same letter. It's going to have, for instance, a subscript in the x direction and a subscript in like the theta direction. Remember, we used to do things with circular cross sections and saying, let's move to polar coordinates, in which, or what we're looking at is we have our cross sectional area. How far away from the center are we? And how much have we, what angle are we? Polar coordinates. So kind of a rho theta. So the shear stress of an object, we'll call it with the subscripts, x theta. Is going to be proportional to the torque you apply. Now we're in polar coordinates, but this again doesn't really matter. These are subtle differences right now. It's just saying it's the torque you apply times some distance you are away from the neutral axis of your rod. We measure in polar coordinates, we measure that distance with the Greek symbol rho over j. This looks familiar, hopefully. Shear stress. So I'm pointing this out because these are the same equation. Stress equals couple times distance over second moment of area. Shear stress equals couple times distance over the second moment of area. Now there are some subtleties. I is the second moment of area in Cartesian coordinates. J is the second moment of area in polar coordinates, but they're both measuring the same property, which is kind of the geometric rigidity of your object. The important takeaway here is that moments, bending moments, and torques are both couples. They're forces times distances. So the stress has the exact same form, regardless of the type of deformation you're doing. It's going to go, the stress will go linearly with the magnitude of the couple, whether it's a bending moment or a torque. It will vary linearly from the neutral axis of your beam to the edge of your beam. So that in bending is usually measured y, where y is sitting kind of right at the neutral axis of your beam, and you'll have that bending will go linearly from away from there. In torsion, it's going to go, remember, if you remember, one of the things you might remember from torsion is if you twist an object, there's no stress along the neutral axis of that beam. That would start at 0 here. If I put in 0 here, this is 0. Bending is the same thing too. You bend an object, the neutral axis, hence its name, neutral, is going to have no stress. When I put in y is equal to 0 here, the neutral axis has no stress. And both of these quantities are kind of modified by how rigid is that geometry. You can remember all the stuff we did in mechanics of materials where you look at like hollow rods that you twist versus complete cylinders that you twist and so on and so forth. Even Hooke's law looks the same, right? Hooke's law is we're used to seeing it's going to be stress is equal to Young's modulus times strain. Hooke's law in shear, same thing. Stress is equal to shear modulus times shear strain. These are slightly different moduli. They're related to each other by Poisson's ratio. So these E and G, if you remember, are connected by the Poisson ratio. One kind of measures the object's ability to stretch or compress, which means kind of go from a rectangle to a longer rectangle. And the other one is measuring the resistance of an object's ability to distort, which means go from a rectangle to like a rhombus. What is the symbol next to T? Good question. This is the Greek symbol rho. Using rho to be my coordinate axis in polar coordinates, where in polar coordinates we would also say I can tell you where I am relative to the center of the circle as a magnitude rho. And I could measure, for instance, how far around the circle I am with an angle theta. Theta going from 0 to 2 pi, rho going from 0 to the actual radius of your cylinder. We change coordinates because circular rods are easier to analyze with polar coordinates than Cartesian coordinates, but they're measuring the same thing, which is how far are you relative to the center of your object. And the center of your object is important because when you apply pure bending or pure torsion to an object, there's no stress here. Oops. There's no stress here. The stress varies linearly from my red dot here out to the edge of my beam. This is mostly a refresher to tell you that your Young's modulus is also the same. It's saying there's a linear proportionality between stress and strain, where in uniaxial extension, this is just like how are you keeping the same shape, but like elongating or kind of changing its area. And shear modulus is kind of keeping the area the same, but distorting the shape. This is a very long-winded way of saying that here's our stress, which looks very much like the stress that we had before. Here's our Hooke's law, which looks very much like the Hooke's law we had before. Our torque, you may or may not remember, is related to with the same type of constitutive law as the one I said before, where up here I said, hey, moment equals amount of curvature times EI. Same idea. Torque equals amount of twist, which is measured by tau. This is probably super confusing because it's very likely that you thought of and learned about tau as a shear stress. I'm sorry. There's also a huge wealth of literature where they use tau to measure the amount of twist, T for twist. And so for right now, this is think of this as amount of twist. Not shear stress. It won't matter too much in what we're doing. I try to use my shear stress always with sigma because it makes the notation simpler. So if moment equals amount of curvature times E times the second moment of area, then torque equals amount of twist times G times the second moment of area. You can put all this together. You can check it on your own, but you probably already can guess what's going to happen here. And what's going to happen is that the strain energy in torsion will scale as Gj times the integral on the length. Well, we can get rid of the scale as we can just put this equal. And so this is going to equal to Gj over 2 times the amount of twist squared integrated over the length. This is the exact same mathematical form as this. Modulus times second moment of area times the integral of deformation squared. So we don't need to spend a ton of time on this. They're basically the same. You square the twist, you apply double the amount of twist, you get 4 times the amount of energy that you're storing in that twisted object. Same thing as if you double the amount of curvature, you get 4 times the amount of energy stored in that bent object. All right. Why am I telling you all this? How is this useful? I think there's a big, I'm going to kind of briefly go on the side here. There's a big feeling, especially among students learning solid mechanics, mechanics of materials, structural mechanics stuff, of like, why don't we just dump all this into a finite element and solve for what we're going to see? And one of the big challenges in that is that whether you know it or not, you're making a lot of choices when you run a finite element solver about what you think is important and what you think you can neglect. For instance, if I was to ask you to go into COMSOL or Abacus or SolidWorks and model a beam, cantilever beam that you're going to pull on, twist, and bend, I'm pretty confident that all of you could figure out how to do that in a little bit of time. You could figure out how to use SolidWorks to make a CAD model of your beam. You could figure out how to apply forces and torques and bending moments. The challenge is, even when you sit down to do that, there's a whole host of things that you're neglecting that you may or may not have chosen to neglect. The most obvious one is you probably neglected gravity. Is gravity there in your model or is it not? More subtle ones are things like, is there a perfect connection between the wall? Is there some friction there? How is that moment that you're applying perfectly distributed along the edge, or is it really applied at a point and you're kind of approximating it as being uniformly distributed? Are there magnetic fields around? Are there any electrostatic, currents, surface tension? Is there any humidity in the air? Is there any kind of absorption of small amounts of water on your sheet that might be present? Typically, we start by neglecting a lot of these things, seeing how our model does, going back and adding stuff in. COMSOL is a particularly great example because it's a multi-physics model. That's its whole thing, is you can add whatever physics you want to it. And the question that you're usually forced to reckon with at some point is, well, which physics do I need to include? And one of the benefits of this kind of energetic approach to structural mechanics is it allows you to write down the various potentials, strain energies, energies that are possibly relevant to your problem, and estimate their magnitude. And that will allow you to decide, oh yeah, that's really small compared to that thing. I can leave that out. Gravity is really small in this case, so I'm going to ignore it. So these energetic approaches allow you to simplify the model, which allows you to justify some of the assumptions you're making either in your analytic calculation or in your computational model. Let me give you an example here. We're gonna end with this example. And we just split strain energy of our object into stretching, bending, and torsion. We'll ignore torsion for right now and just think about stretching and bending. Oops. So you can gain a lot of intuition just by looking at the relative orders of magnitude of the various energetic quantities that describe your structure. So we know that our stretching energy is proportional to the elastic modulus. Let's scroll up to remind ourselves. It's proportional to the elastic modulus times our strain squared times our area times the integral of the strain squared over the length. I'm going to write this out as the cross-sectional area of a rectangular bar, which has an area of h times b. And we already said that, well, we can treat that integral over the length as going to give us something that's going to have a unit of length to it. So we can say that this is really like EHB L strain squared. Our bending energy, we can write down in a similar way. We just did this. And it is here. And our bending energy has a slightly different form. It takes the form of E h cubed b integral of curvature squared dx, which is E h cubed b L kappa squared. So what we can do is we can say, let's compare the relative magnitude of stretching and bending in an object. So we can just say, well, let's take the bending energy over the stretching energy. And this is going to look like, this is just a lot of algebra, EH cubed B L capital squared, that's our bending energy. Our stretching energy is EH BL strain squared. You can see pretty quickly that we're going to lose the width, we're going to lose the length, we're going to lose the thickness. And when comparing bending to stretching, what we find is that the relative magnitude of bending to stretching depends on only three parameters: thickness, which is squared, times the relative magnitude of curvature and strain squared. The most important term out of those three is this one. And what that tells us is that if your structure, let me say it a different way. As your structure gets thinner, the cost to bend that structure relative to the cost to stretch that structure goes down. And it goes down real fast because this quantity is squared. The smaller h's, the easier it is to bend relative to stretch. Objects like to minimize their total potential energy. So they want to find the deformation that takes the least amount of energy. And what this tells us is that thin objects are really easy to bend and really hard to stretch, because this quantity thickness here enters as an h squared. Let me write this down. Thin objects are easy to bend and hard to stretch. And look around you, at least for the folks in here, every one of them has a jacket that is crumpled up on their chair. It's folded over itself in 25 different ways. It's so easy to kind of take your shirt and bend and crumple this thing. It's remarkably easy to take your sheet of paper and just do this to it. It takes no force at all. And yet if I take this sheet of paper and I try to stretch it, like, I'm not physically strong enough to do this. If I was able to stretch it much at all, it would break. Thin objects don't stretch. They deform by bending. This is really important for a couple of reasons. One, if you're trying to do a calculation with pen and paper, what you'll find is that oftentimes people will say, or they're going to make an assumption. This is the word you'll see the assumption that they make. You'll see that they'll say, let's assume our beam is inextensible. They're saying we're only going to solve for deformations that involve bending. We're going to not only say that stretching is small, we're going to say stretching is exactly 0. It's not stretching at all. If you remember from mechanics of materials, you probably calculated the buckling load of an Euler beam. One of the first assumptions that you use when calculating the buckling load of an Euler beam was that that Euler beam was inextensible, such that you're saying I'm going to load it, it's not going to change length. If it deforms at all, it'll bend. Thin objects are easy to bend and hard to stretch. This type of analysis also allows you to simplify your computational models. Now, you typically wouldn't throw away stretching energy if you were doing something in COMSOL or Abacus or SolidWorks. But if this was a different type of energy, like a gravity or something, you might say, oh, for my class of objects, if my length scale is small or big, I can neglect this term. That means I can run my simulation without including, say, gravity or whatever the term that is small. But this actually has a more profound effect, and it goes back to what I said in the first class, which is that thin objects are typically stiff, like you saw with that sheet of paper, remarkably stiff in tension. But they're prone to instability. And this is one of the big kind of conundrums for structural engineers, is that you're generally trying to drive down your components, make things as thin as you possibly can, because you gain that stiffness while also gaining ultra lightweight reduction of either material, so that saves you money, or reduction of mass that you have to transport or move around, which also saves you money. So you're generally trying to see if you can make things as thin as possible while keeping that same stiffness. But as you make things thinner, you have to remember that thin objects are easy to bend and hard to stretch. And what that means is buckling instabilities are basically objects bending when you don't expect them to bend. What do I mean by that? Let's go back to Euler buckling. Euler buckling doesn't make any sense if you just think about a beam in which I'm going to take this object, I'm going to try to shorten its length. Like I'm going to literally take the span of this object and try to decrease the length of it. So all I'm trying to do is compress it. Stretching and compression are the same, they're just different signs for the same deformation, right? It's stretching, compression, stretching, compression. When you try to compress a thin object, you're trying to shorten its length. And an instability emerges because the beam says, I don't want to shorten my length. That costs too much energy. Is there a cheaper way for me to deform? And what it finds is, yeah, there is a cheaper way for me to deform, and it'll bend. And that's the problem with buckling instabilities, is that you get bending when you're not trying to get any bending. I'm not applying a moment here. I'm applying a uniaxial compressive force. It should shorten the object. And it does for a little bit, and then it buckles. This being prone to instability is the direct result of the fact that thin objects like to bend, and they will find a way to bend as opposed to stretching all the time. Anything where you see instabilities occurring, what you're seeing is, in structures, what you're seeing is an object that found a cheaper way to deform. And thin objects, it's always cheaper for them to bend than it is to stretch. So that's the takeaway I want you to have here from today's lecture, is a little bit twofold. One, if you remember nothing else, remember this, because this will help you as an engineer for years to come. if you can remember two things, the second thing I'd like you to remember is we figured this out all on our own just by calculating the energy of these certain types of deformations, stretching, bending, torsion. And just by comparing those energies, an equation popped out that said, well, if my object has a small h, then this whole quantity is going to go to 0, which means the numerator over here is going to be a lot smaller than the denominator. Therefore, I can make this statement in pink here. What we're going to do next class is look at a couple of other types of deformations. Again, using the scaling approach. We're going to look at when does gravity matter for a structure? And we're going to look at when does a fluid that's touching structure matter. And what I mean by matter is when does that thing, gravity, fluid, start to deform our structure. I'm going to send you a review paper to read. This is one of those times where I'm the professor that wrote the paper and I'm making you read my own stuff. Sorry, but I think it's useful. And I don't think it's overly technical in the first few pages. The point of this, me asking you to read this, is twofold. The first part of the paper goes through some of these scaling arguments in the same way I'm doing it here, to talk about various phenomena that you see every day around you. And the second part of the paper kind of gives you a more modern view of what structural mechanics is. I think structural mechanics, people think of like stodgy old dudes 300 years ago, like looking at beams when they bend. And right now there's a ton of active research on structural mechanics. Everything from how do we model hair, and how does the ability for us to model hair affect Pixar movies like Brave and Moana, in which those movies appeared because mechanics people figured out how to model hair, hundreds of thousands of pieces of hair interacting with each other, and computationally calculate that really, really fast. Whenever computational folks figure out how to do something fast, Pixar makes a movie about it. They figured out how to model granular materials. Granular materials, if you take their mass and make it really, really small, turn out to be a really great way to model snow, and you make frozen. The ability to kind of connect what we understand and what we can compute as mechanicians nowadays has far-ranging impacts, from the development of stretchable electronic devices to metamaterials that have behaviors that don't naturally occur in any material that you can find, but we can engineer their whatever behavior we want into them. And metamaterials, at least in the sense of mechanical metamaterials, is just a fancy way of saying structural mechanics. It's a new way of putting a new coat of paint on an old problem. So structural mechanics is, you're going to have a lot of things like this in this class, but the field of structural mechanics is incredibly rich right now. So I'm going to ask you to read this paper. I hope it's not miserable. It shouldn't be too difficult to read. And what I'll ask for you to do is to come to class on Tuesday, maybe jot down 1 or 2 questions or discussion points about it, so we can talk about it here. This, I hope, will accomplish 2 things. 1, will get you excited about structural mechanics because I think it's awesome. But 2, to maybe break some of the silence inherent to a 9 a.m. mostly virtual Zoom class. And so please, I'll send you an email with this, and I'll post it on our website when I get back to my office. Read that paper and come prepared with a question for me. And this will be like the first, basically, homework assignment, if you will. But I just think of it as a way for us to kind of motivate what we're going to be doing. Sound good? All right, thanks everyone. Have a good weekend.
Hey, Professor.
Yes.
I couldn't find the notes from last class's lecture on Blackboard or on your website. Have they been posted somewhere yet?
Yeah, I said this at the beginning of class. My computer died in my office on Tuesday, and I didn't do anything to get any of the course stuff up. I have my laptop here today as a stopgap, and so I should be able to get all those things up today. So yeah, they're not there yet, but they will be hopefully by the middle of the afternoon.
Just making sure we're not out of the loop. Take care and have a good one.
Thank you very much.